Okay, so here's the video I promised you so that you guys have something to chew on while we don't have class. So the next chapter we're going to work on is the chapter on antiderivatives. So just quickly, even though this starts to get old hat by this time, recall that given a function f of x, so pretty much all the functions we can deal with this in this course, we define f prime of x as this limit, the limit as h goes to 0, of f of x plus h minus f of x all over h. And we say f prime of x is the derivative of f of x. And that is if the limit exists, right? It doesn't exist for all functions at all points, but most of the functions we deal with are pretty nice. And then we have an interpretation for the derivative. The derivative gives us the slope of the line tangent to the function, tangent to the graph of the function at a point. So the derivative is like a slope function or a rate of change function. And also f prime of a, the derivative evaluated at a point, gives the instantaneous rate of change of the function at that point. So we've spent quite a bit of time calculating derivatives and interpreting derivatives. And here's sort of an obvious question. Given a function, or just given the derivative, can you say what the original function was? In other words, if I tell you what the derivative is, and remember the derivative is your rate of change function, can you tell me what the original function was? So, for example, if you know that f prime of x is equal to 3, what could f of x be? Well, I'm sure you're screaming at your computer right now saying, John, I think f of x could be equal to 3x because if I take the derivative of this function, f prime of x is equal to 3. But notice that f of x could also be equal to 3x plus 2. It has the same derivative. Or f of x could be equal to 3x plus 17 e to the pi. Or any other crazy number I wanted to add. In other words, I could add any constant onto here. So there's a way in which finding the antiderivative is loses information, because when we try and go backwards, in other words, when we try and reconstruct the original function after taking the derivative, we lose any information about the constant on the end of it. So let's just do another quick example. Suppose I knew the derivative of some function was cosine of x. What could I say about the function? Well, I could say f of x, one function that would work is something whose derivative is cosine would be sine of x. Well, that would work. But so would f of x equal to sine of x plus 17. I don't know why I always use 17. It seems like an ugly number. Or f of x equals sine of x plus 75 times 10 to the 35th. It doesn't matter how big the constant is. Once you've taken the derivative, when you try and go backwards, you lose information about that constant. So let's introduce some language here. Given a function f of x, we call capital F of x here an antiderivative of f of x if f prime of x is equal to f of x. Now I know that sounds like gibberish, but recognize that I'm distinguishing between capital F of x and f of x. Maybe I should say capital F of x with an accent of some sort. So here's an example. If f of x is equal to 1 over 1 plus x squared, then an antiderivative for that function would be tangent inverse of x. And this leads to actually several interesting questions. First of all, does every function have an antiderivative, or only functions that we've already taken the derivative of, right? Can I just give you an arbitrary function and get an antiderivative? And another question is, does the antiderivative have a nice interpretation in the same way that the derivative did? So given an arbitrary function, if I find its antiderivative, does that tell me something about the function? Well, it turns out that it does. We're going to have to do quite a bit of setup to make that work. Another thing you might be asking is, well, does the antiderivative have a limit definition in the same way that the derivative did? And the answer to that is yes, and we will develop that, but not in this chapter. You don't really need to break out that limit machinery to think about antiderivatives, because all we're doing at this point is trying to figure out, sort of go backwards from doing derivatives. So a little more vocabulary. We define the indefinite integral of a function f of x, and we use this big S notation here as the most general antiderivative of that function. So how do we think of the most general antiderivative? We take any antiderivative of f of x, and then we add an arbitrary constant onto it. So the indefinite integral of a function f of x is the most general antiderivative of that function. So here's something you may have thought of already, but every rule for derivatives gives rise to a rule for indefinite integrals. So for example, the power rule. The power rule, we know, allows us to take the derivative of any power of our variable, any power of x. And it's a simple rule. Derivative of x to the n is n x to the n minus 1. Well, we can think that rule backwards, and that gives us a rule for antiderivatives, which is the antiderivative, or the indefinite integral. So we'll do the most general antiderivative. The indefinite integral of x to the n is what? Well, when we took the derivative, the power went down, so we're going to undo derivatives, so the power will have to go up. And when we took derivative, we multiplied out front by the power. When we do the antiderivative, we're going to have to divide out front by the higher power, and that's because, notice, if I took 1 over n plus 1 x to the n plus 1, and I take its derivative, I get what? Well, I multiply n plus 1 out front, so n plus 1 over n plus 1, so that's 1. X to the n plus 1 minus 1, which is x to the n. So you can always check your rules for antiderivatives. Remember, this has to be an antiderivative of x to the n, and then we add an arbitrary constant. I'll make another quick video about some applications of antiderivatives we can do for an area of math called differential equations, and I'll send that out shortly.